Hello, everyone. My name is Andrey Borodin, and welcome to my talk, Tricks from In-Memory Databases on Build DevCon. I'm a Postgres hacker. I'm mostly working on enhancing Postgres, developing its ecosystem, and working on core of Postgres, and of course on some extensions in Postgres ecosystem. And of course, Postgres is not in-memory database. Postgres is traditional database that, of course, uses main memory. But well, I want to make Postgres better, and that's kind of a difficult mission because there are a lot of Postgres hackers all over the world who are working on doing Postgres better, and we constantly evaluate new ideas. In this talk, I'm going to investigate some ideas from in-memory databases and try to adapt them to make Postgres better. I'm not alone working on Postgres. Here is my team at Yandex Cloud. We are based in Yekaterinburg, and most of us are Postgres hackers. So, if you want to make a database, you work with fast registers, which are relatively small, bigger caches, L1, L2, and L3 caches, which are bigger than registers, but still measured in kilobytes and maybe megabytes. You have main memory, and main memory up to several terabytes on a server, and a block storage, which could be of many petabytes, but usually it's still on a scale of tens of terabytes per server. And you kind of want to build a system which works with the performance of CPU registers and caches, but on a scale of block storage of disk devices. And that's the basic idea of information system to work in this hierarchy. In cloud, you can add one more layer. You can talk about S3 or Google Cloud Storage or network object storage, some network service which further increases latency and provides you with bigger capacity, and like some durability problems are solved there else. Just like with another levels of this hierarchy. And it's interesting that levels of this pyramid are very resemblant. In a sense, cache is organized in cache lines, main memory organized in pages, block storage is organized in pages too, but kind of different pages, usually bigger than memory pages, and network object storage have to be organized in bigger chunks due to bigger latencies. So the key observation here is that algorithms for cache line friendliness are very similar to page management and buffer management in traditional databases. So if you have a program which is not doing any I/O, what can it spend time for? Obviously, it can spend time for cache miss. At some point, we tried to dereference a pointer and see what data is there. And it's not in caches. We have to go through memory controller to DDR or something like that. Also, you can have some syscalls. Basically, I/O will go to syscalls, but even reading current time may require a syscall and other stuff. Also, you can spend some time in branch misprediction. Modern CPUs are very, very neat, and branchy code with unpredictable branching takes time to execute. And also, we can spend time in lock acquisition, which is a kind of cache miss. So we have some volatile cache line, which is accessed from many CPUs, which concur for this cache line and try to steal it from each other. How much time all does it takes? I suggest you to look to a website which is called Latency Numbers Every Programmer Should Know. And basic things that you should know about these latencies is that they do not change too much. You can spend time just one time, inspect these numbers, and just note that like memory got better, but main memory reference still takes same time, but reading 1 MB is now seems to be much faster than 20 years ago. Commodity network got better, but frankly speaking, no one is doing databases via commodity networks. And disks got better, like magnetic disks got much better. But frankly speaking, fast databases do not use too much magnetic disks. Other numbers did not change much at all for 20 years. Despite having a new, fresh, faster MacBook every year, servers are working on the same speed with same problems. We still have to go around that memory hierarchy. And we have to build our database on top of this memory hierarchy. And there is a whole cluster of databases that are called in-memory databases. And this whole track of build.com is devoted to these in-memory databases. They are extremely popular for their use cases. Some of them even take their name from memory, like memSQL, which is now a single store. But what's important about this cluster of databases is that they highlight their limitation. So, of course, Postgres or MySQL or MS SQL or Oracle, whatever, these classical databases use memory too. But in-memory databases can store data only in primary memory. And what key ideas can we take from these databases? There are lots of them. And every PostgreSQL can say jokes that just use unlogged tables. They are not durable, so they don't depend on disk that much. That's only a joke. This unlogged tables is just unrelated technique to performance of memory databases, which might be logged, by the way. And there is a joke from in-memory databases. Can you do a database read in microsecond? Or can you do a write in a microsecond? And for classical databases, which have statistics, which have line, which have a very complex syntax to parse, and many layers of interaction, the answer is no. That Postgres just don't speak in microseconds. Yes, you can do sub-millisecond queries, and that's very good. And possibly you can have a sub-millisecond writes, but optimizations bringing performance below millisecond, 1/1000th of a second, is very difficult in Postgres. And for many tasks like session state management, you actually want microsecond reads, microsecond writes. And one well-structured source of ideas is, of course, academic research. In this sense, I can recommend reading about Umbra. Umbra is essentially database made by scientific team. Today we have a production version, CedarDB, but Umbra is interesting in a case that it's more about trying ideas and evaluating ideas. So I've read a paper about Umbra and tried to apply their ideas to Postgres hacking and test them in Postgres. And the basic idea of Umbra is high specialization. This is rooted in their previous database from Munich University, Technical University of Munich. It was called Hyper. And the basic idea is extensive application of just-in-time compilation. So the query is basically a program, C++ program that is compiled into native code to be executed faster. And this idea sounds viable. So we have some just-in-time compilation in Postgres, but Postgres just-in-time compilation is very controversial. We even have talks about disabling by default just-in-time compilation. And that's because just-in-time compilation, in my opinion, is done in a wrong layer of abstraction. Postgres is super generic. In a sense, in normal database, you can create user-defined function, and that's like general approach. But in Postgres, you can define user-defined types. Basically, you can say, hey, here is a function to parse string into this type. Here is a function to add two values to appearance of this type. And here is a way to compare datums of this type, and so on. Basically, you are providing a function which works with just like several bytes, maybe 4 or 8 bytes. And it's these functions can be very hot in the sense that they are called many times, and switching to compiled code at this place might be just wrong. There is another opposite approach which is taken by ClickHouse. ClickHouse compiles into several gigabyte sized binary. So it's huge. There is a lot of assembler code inside ClickHouse server binary. Why? Because like every data type is actually database itself. It is compiled functions that are doing scanning. There are compiled functions that are adding to columns. There are compiled functions which are doing aggregation, and sometimes there are even cross-compiled specialization for summing two columns of different types. So if you have 10 types and you are going to specialize function that adds two columns, you have to precompile 100 of functions that just add two columns. And this approach is totally fine for ClickHouse. Like ClickHouse wants to be faster, that's why they specialize their code, but not in a just-in-time compilation way, but in pre-compilation way. So they have this code before they actually have data. This approach is somewhat present in Postgres code base. For example, we have a specialized template for sorting. In a code, if you want some sorting, say you want to sort 32 bits integers, like here, you have a comparison by two pointers, but this function, sort in 32 ascending CMP, won't be used by actual sorting function. It will be compiled in the template, and compiler knows that this sort in 32 ascending function will not have, will always use this comparison function. How does it affect performance? So if we use a generic sort provided by libc, we see that sorting 1 millions, see that sorting 10 arrays of 1 million random numbers takes about 1 second. If we specialize sorting function, just not use generic function, sorting sorting takes 300 milliseconds less. It's faster on 1/3, and that's a lot actually for performance. Many places in Postgres actually use this technique. For example, here is a commit by Thomas Munro, which specializes sorting of buffers that need to be flushed by a checkpointer. So buffer number is always of the same type. We don't need to use generic function. We can specialize here, and we see here even larger improvements for some specific operations that are done by specialized code. So this reprocessor hacking might seem like decades old now, but it still works, and works on relatively new tasks. But what if we specialize on actual types in actually hot operations, like primary key B-tree indexes? Here is a binary search which is employed to look to B-tree page. So we have a scan key here. We are looking for this scan key on a page, and we are inspecting tuples between high and low, and new mid is computed like something in between high and low tuples. We see here generic functions that is comparing keys at offset numbers, but we can specialize for several data types. Normally for primary keys, we use either small integer of 4 bytes or big integer of 8 bytes or very big integer of universal unique identifier. By the way, I recommend version 7 and Postgres 18 have my implementation of UU7. And that ought to be enough for everyone, you know. So if we look into B-tree code, there are two places where we encounter cache miss, and two places that take time to actually execute. One is deforming a tuple, so just extracting datums from a key or index tuple. What does it mean, deforming? Tuple can have several datums, so it can be can have index on multiple columns, and the code have to account for it. And there might be some nulls before the extracted keys. But when you use it for only primary key, that is much easier. You can just say that add byte of set 8, let's extract 4 bytes and beat it. And another place where we spend time is a comparison. And we just can compare two datums. Just say, hey, I know that it's just 4 bytes, and we can compare assigned or unsigned integers and beat. And if we do so, I've created extension. I've added it into Bloom extension, and this index I called it XB3. So we have unlogged table X and unlogged table Y, X with XB3 and Y with a regular B3. Let's insert some random numbers, and you see similar performance improvement as we saw in previous specialization of array sorting. By the way, array sorting is now committed into Postgres 18.2. That's promising, but that's not in core index. It's just an extension. Maybe we can specialize operator class of B-tree to involve this specialization. Like currently, operator class provides you a function to compare two random two numbers, two datums of specific type. But what if operator class would provide a compiled function to inspect a page that could bring this 20% of performance? Another idea from Umbra is their very neat buffer management that is rooted in Lean Store and previous works. And basic idea is avoiding indirection at all costs. What exactly costs do they take to avoid this indirection? They have variable size pages. In Postgres, like you can have variable character, you can have national variable character, you can have text, and all that kind of stuff. And we usually recommend just use text for any textual data. And it can be arbitrarily large up to 1 gigabyte. But like 1 gigabyte doesn't fit on a Postgres page of 8 kilobytes. And you can store much bigger values. This technique to solve this problem is called the oversized attribute storage, or TOAST for short. So we can we can create a TOAST identifier on a B3 page that is referenced, sliced text somewhere else. In Umbra, they just use bigger page to avoid indirection and place their big tuple on these exact pages. And they are using different operating system. Like Postgres is managing its buffer pages on its own. We have our eviction algorithm. But Umbra is reusing operating system capabilities, which is actually good for us to evict data from page. Another interesting technique that they use in buffer management is pointer swizzling. So when you have a tree index, it must be represented in storage to make it persistent, but some pages can live in main memory and employ direct links. In Postgres, we use for this shared hash table. So when you have a B3, you like pages of B3 reference to each other by block number. And when a leaf level of B3 is referencing some items, it's using heap page block number. And this is a way of indirection. If you want to convert block number and offset inside a block number, you have to check, is this block number in my shared buffers? If not, we're going to read it. If yes, let's take it. In Umbra, they can just follow a pointer without using this contended shared hash table, which is like a great bottleneck actually for Postgres. To achieve it, they use Swiss pointer. So pointer can be essentially page address or regular pointer in main memory, and they unswizzle them when they evict a page to file system. But that's relatively easy because they have to unswizzle just one pointer. Because Umbra is using a B3 version, which does not need many pointers on the same page. Essentially, when you unswizzle, when you evict a page, you have to unswizzle a pointer somewhere else. And B3 looking model in Postgres requires many pointers to the same page. We have a linked list on each level of B3. But I tried to prototype pointer swizzling in case of just trying to save access to shared hash table. I decided that I can just add some information in the tuple about a buffer that was used to store this particular, to store page that is referenced by this particular tuple in a B3. Essentially, when I'm trying to read the buffer, I also supply buffer manager with a candidate buffer that was used in previous buffer lookup. That can save us time for locking hash table and searching in that table. I've done a simple benchmark. So I create a table with random numbers and with several indexes. And let's see how much time does it take to insert some random numbers into this table. So here's the relative performance, relative time to insert numbers. If this time is above 1, that's bad. If it's below 1, that's good. So we see there is a working set which fits into shared buffers when this technique can provide up to 10% of improvement. So up to 10% of time less spent on inserting tuples. But when I tried it on a server build, I observed a bit higher numbers, and the effect was not that clear. So it's kind of a statistically insignificant effect, and I decided not work further on this pointer and Swithen technique. But it's still worth discussing. Like, there are two generic questions that we must answer when we are designing pointers Swithen for Postgres. What information can be stored? So this is a basic computer science trade-off. Space for complexity. We want to cache some information that must save us future work. And first, what we want to answer is what exactly information do we cache? And when we have this answer, we have to answer second question: where do we cache this data? I used caching on pages, and that's not a good idea because these pages will eventually be written on a disk, on file system, and that might be wasted storage. Another idea is exploiting page layout and trying to make it more cache friendly. It's based on very old, 20-year-old paper about partition attributes across page layout. Pax, or partition attributes across, is also used in Umbra too. But I decided to go and inspect history, and there are some neat pictures in old page. So regular pages with tuple, they call it NSM, N-array storage model. And Pax page is when you try to pack datums of same attributes together. That means that if you do not access the whole row, but only some projection of a table, it will be much faster because you will save some cache line access on columns that are not accessed. In Postgres, we have all the infrastructure for this. Postgres page consists of line pointers and tuples that are written from a backward footer of a page. Someone might even say that it's not CPU friendly because when we are doing ascending scan of line pointer 1, line pointer 2, line pointer 3, we will go addresses from backwards. And CPUs don't like this data access pattern. But still, we can move tuples and even deform tuples on a page. And I decided just to relocate some tuples, trying to make it more effectively. The first thing that came to my mind is just try to use non-temporal prefetches, to use cache prefetch of two other candidates that might be used in a B-tree. So here we have a accessed key with offset number mid, and two possible candidates that will be accessed on the next scan. This is generically a prefetch of a B-tree scan, cache line prefetch. and it's relatively cheap to implement, but it wastes some of cache. It creates more cache pressure because we have to prefetch both tuples. One of them will not be accessed. Another idea is that we are accessing tuples on a page in some pattern, and this pattern can be optimized. This idea is called Eitzinger layout. There is a very neat paper, a scientific paper, which I highly recommend to read. And the paper shows very impressive results for searching for binary search in an array. But we have a page. Essentially, how can we try to locate tuples on a page to save some cache misses? We can try to use Eitzinger layout, which is just storing layers together. In this case, tuples number 2, 6, 10, and 14 must be nearby because 2 and 6 can be prefetched. So Eitzinger layout must be prefetch friendly. Another idea to just store it in order scan. So if we take one of just lower branch of binary search, next tuple have chances to be in cache already due to previous cache miss. And the other technique, which I called Van M. de Bolos technique, is when we store several nodes together, so some part of subtree together. In this example, if we store 4, 2, and 6 together, this is Van M. de Bolos layout. So we have a cache miss on item number 4, but this cache miss will fetch for us items number 2 and number 6, which will be needed in next iteration of binary search. I implemented this for B-tree, but the problem is layout strategies are destroyed with every vacuum. So they are destroyed with any insert in a page, and they are built only by vacuum. And I tried to test it with read-only queries, and here you can see that prefetch worked well. So I just used lookup queries, and prefetch works with data in tuple addition order, and Eitzinger layout somewhat works without prefetch. So prefetch contradicts two strategies. I don't have some explanations for these results, but I see here that we can add several percents of performance, which is not that much, and maybe just stacking many such techniques together can bring some performance. Finally, the Umbra have an idea of optimistic buffer locking. I tried, but I failed to implement it in Postgres because we have too many places that are accessing datums of pages. The idea is that we scan a page without taking a lock, just checking that no one is modifying page right now, but we have to take a buffer pin, and we compare LSN before we did a scan and after we did a scan. But scan is done by a lot of places in Postgres, and that's problematic for prototyping this technique. And what we skip is just we skip one-time buffer lock. The problem is that we still have to take a pin on a page, and the pin technique actually is somewhat resemblant to this technique. So when Postgres scan a page, it takes tuple pointers, and maintaining a pin on a page, it can unlock a page at all and just give pointers to these tuples to scan and so on. So we have a lot of ideas in memory databases, and they are not about elimination, but in optimizations that are specific for caches and memory access patterns. These ideas together can bring several percent of performance. Maybe Postgres have just different bottlenecks, but overall, I think it's worth watching for new ideas, and the idea of specialization can definitely work for Postgres, and I'm going to work on this further. Thanks for watching, and I'll be happy to answer all your questions.